There we go. Are you? I have to always ask that. What's the, can you see the screen?
You got it.
Yeah.
Okay. So let's first talk about the first slide was just me. Not a big deal. Spectrum. This is the US FCC's frequency allocation chart that I don't think anybody actually uses. No, it's just way, 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 way too much information. Just realize there's a whole lot of spectrum there to play with. And in Wi-Fi, we're going to deal with just some really small little slivers. So one of the slivers we're going to deal with, and it looks big here because I spread it out, but on the frequency chart, it's a little teeny sliver, is 2.4 gig. And 2.4 gig has been, well, originally like forever ago, 80 years ago, so whatever, they call this the junk band because there's a lot of things that exist in this frequency that cause issues. So no one used it for a long time. And then they finally came around and said, well, we'll dedicate it to the industrial, scientific, and medical. And this is where we started 2.4. It was unlicensed and it's harmonized across the world that anywhere in the world you can have access to this 2.4 gig. We use it for Wi-Fi on the top, Zigbee in the middle, BLE and Bluetooth down at the bottom. And there's different ways you can slice up this same amount of data. The same amount of frequency. It's used by Wi-Fi in larger chunks and in Zigbee in smaller chunks and in Bluetooth, even smaller still chunks, but we're all sharing that same frequency. Note the green and blue and kind of yellow up on the top for 2.4, how channel 1 and channel 2 have a little guard band in between them. So between channel 1, there's a guard band, and then between channel 1 and 6, there's a guard band, and there's another guard band between 6 and 11. Those guard bands are there to keep from bumping into each other. On the other hand, 1 and 2 have a massive amount of overlap, and because of that overlap, when you have 1 and 2 at the same time, you get much, much lower throughput because they're sharing that frequency and they back off a different way. This is old stuff. We've been doing 2.4 for 20 years plus in dealing with Wi-Fi, but just want to do a little review there. Another set of frequencies we used in Wi-Fi now is the 3.5 gig. They're actually 3.6, 3.7 kind of range. And we use it for private LTE, CBRS, and it's kind of in between the 2.4 and the 5. And so most of our phones, handsets have the ability, because of the size of their antennas and the chips that they're using, to be capable of using these frequencies. And so check your device, but most devices today are capable of being CBRS available. Then we get to the 5 gig frequency, big, huge chunk of spectrum. We've got a slide later showing the differences in the amount of spectrum, but we have a ton of spectrum up in 5 gig. This chart has a lot of details in it. And if you look at it, drill down, there's a lot more there. At the bottom, it says wavelength, and it shows the size. There's one of those on the 2.4 as well. And then below that, it says free space path loss at 1 meter. And this is a calculation. In a little bit, I'll show you what the calculation actually is so you can do your own. But each frequency that we use, each channel, has a center frequency. And so I also added to this chart what the free space path loss is at 1 meter. And if you know what 1 meter is, then as you expand it out, you can just follow the formula and it follows along. But wanted to show here that on the far left side of this, at 1 meter, it's a minus 45.74. And all the way at the right side, it's a 46.84. So there is some differences. If you're in a higher channel up in the Uni 3, you're going to have slightly less coverage just because that frequency is physically smaller. And so it has a greater loss over the same distance. So your Uni 1 actually can be used and travel a little bit further, and the details are on there. So this was just review time to look at what those look like. We can add a 6 gigahertz, and all of a sudden you're like, whoa, so much 6 gigahertz. Yeah, there's a whole bunch. You could see that on the left side, there's a little red line with those same numbers of free space path loss. And they continue, but since this is 1200 megahertz wide, there's a lot of spectrum. And so by the time you get to the far end, it even loses more. So I'm going to try to show these to you a little more visually in a second. At the top, you can see the wavelength. There's sizes on the left, middle, and right. And the very bottom is the EU ETSI version. Sorry, you guys, you get less frequency. It's okay. You have, at least it's more than you had before. And we have 6 gig to play with. So now, if we zoom in, you can see there's details on each of these things. There's a little, actually literally a guard band here on the left side. There's the wavelength at the top. There's the specific frequencies of where the edges are. And then there's also these little kind of gray squares along that talk about the preferred scanning channels. So you can see that they're a little separate. I initially had them just in bold up above with the numbers, but they weren't like in your face. So we added some extra information. So this just we're gonna review a little bit about the frequencies we have to play with. Before we talk even more, you need to realize, I already understand this. I'm sure Jim's got it down. You need to be able to convert dB to normal math, like in your head quickly. A couple days ago on LinkedIn, Chuck Lukaczewski made a comment about some antenna patterns and said, these are in dB. That doesn't show you how far they go in the real world, because most of us aren't very good at converting log scale in a number, dB, into real world distances in our heads. One, as humans, we're not really good at log scale. We live through it all the time. Like our hearing is actually in log scale, but our brains don't work that way very well. So you need to kind of practice, and you should be able to hear the word dB and know what it means in the real world. So just to put Heather on the spot here, if I say, I'm going to give you a 6 dB raise, how much more money would you have for your wedding?
You said 6, so I'm going to go 6 million. That's what I want to hear.
That's what you want to hear. It's still a really good number. It means you get 4 times more money than you have right now. Now that would be a good raise, but it doesn't sound that way when you just hear the word 6. Well, it's only 6, but it's how the math works behind it. It means 3 dB would double, and another 3 dB would double again. So 3 times 3 is 4, or it's a 4 times raise. So those are the things that you should keep in your head and be able to do easily and quickly on your own. So now let's look at this chart, and we're going to talk about it because when we talk about the differences between 2.4 and 3.5 and 5 and 6 gig, they all follow this same curve. Now, to keep it, I had one of these curves and had all the frequencies on it, and it was really too crowded. So I pulled it down to just 2.4 and 5 gig. But we can do the same thing with any frequency we want. In fact, I've got a table. I'll show you where this data came from. I'll even give you the formula I used. And please, I hope you make your own Excel spreadsheet that can help you understand how this works. Now, this was originally designed to help people understand why, when you're going to be doing a measurement of RF of a wall thickness, you want to know what the RF attenuation is of wall. You have to have the thing that's making the RF. Usually we carry a little portable AP or something that's going to be making the RF. But it needs to be, I say, at least 4 meters away from the wall you're trying to measure, because if it's closer, what you'll be measuring isn't the wall, you'll be measuring the huge change in free space path loss that happens in that first little bit. So people used to go and take a little access point and put it next to a wall, and then go on the other side of the wall and measure what the RF loss was. And they go, oh, it's this much. The problem is when you're inside that first meter, if you just look at 3 centimeters, that's on the far left, if it's 3 centimeters away, that's not very far, you've already lost 10 dB. At 6 centimeters, you've lost 16 dB. So if you're measuring something and it's close to the wall you're measuring, you're actually measuring the distance, not the wall, because it falls off so quickly. In fact, I used to show a demo of this very thing. If you stand there and you breathe, and your hand moves 2 or 3 centimeters, that could be a 10 dB loss difference if you're close to the thing. If you're out 4 or 5 meters away, you can move half a meter and it's hardly going to move at all. So this is showing a couple things. One, I wanted to focus, when you're measuring RF, make sure you're far away from it where it starts to flatten out. The other is there's this differential between the two. The differential between 2, 4, and 5 gig, and I'll show you the math in a second, is constant across the board. If one's dropping, the other one's dropping with it. If we compare this to 6 gigahertz, 6 gigahertz would be slightly less, and we can look at the numbers, but it follows the exact same curve. Every frequency follows the same curve. Another little side question, and I'll pick on Jim this time.
Uh-oh.
If you knew that the RF that you sent from here, and you do ham stuff, so you know people send signals up to satellites. What if we had a satellite sitting halfway to the moon? Oh, there you go, right in your hand.
Yeah.
We had a satellite sitting halfway to the moon, and you could hear it on your handset.
Yeah.
It'd be a big sound. What would the dB loss be if you then took that satellite all the way to the moon? Now we're talking a long way. So halfway to the moon to all the way to the moon, what would the difference be?
I think you'd lose about 6 dB. Go about
Exactly.
double
And so
the distance.
You have this idea that, oh, it's really far away, it's going to be different. But as you get in this long tail, it actually plays off pretty good. You could go, if it took 100 dB to get halfway to the moon, it would only take 106 dB to go all the way to the moon. So it can work in our favor, but it's also sometimes if you wanted to go that much further, you'd have to increase the power. So the other side is, if it was 100 dB to go halfway to the moon, you'd have to increase the power 6 dB to go all the way to the moon. And we have proof of this because NASA sends things out way past the moon, out past Jupiter, and we can still receive radio signals. So this free space loss curve and understanding how the gap works is going to help us when we get to this analysis and difference. Here's the actual formula, and you can follow along. It's free space path loss, and I put it in Excel format. So if you just wanted to copy it, you can put it in Excel. You just need to change where it says distance in meters and frequency in megahertz and make those equal the left column for distance and the top column where it says, little word says meters, but to the right of that is the actual frequency in megahertz. So then you get this little table. This is the table that shows that free space loss. Note, I started with 1 meter, but I also went backwards to show that really super steep curve at the beginning. But you could recreate this literally in a couple minutes in Excel and understand this. So play around, change the frequencies, etc. I also threw a little 60 gigahertz all the way on the right side because 60 gigahertz is a thing. A lot of people are using it nowadays. And there's a lot of stuff we can pull off with 60 gigahertz. Just realize it has a huge loss. On the other side, it's really small, so we can get some super high gain antennas in a very small package. So let's compare frequencies. On the top bar is 2, 4, 5, and 6 gig based on how much bandwidth we have available. And it's obvious by this picture, we have lots more bandwidth than 6 gig. Everyone, we've talked about this, people talk about it all the time. 80 megahertz in 2.4 was very limiting, especially because we only had 3 channels. And now we have more in 5 and even more in 6 gig. But the other thing I wanted to focus on was what's the size of these, because it matters. And it matters a lot in how we're going to be designing, how we're going to troubleshoot, how we deal with how Wi-Fi works. So the size, the physical size of the wavelength of 2.4 is 12.5 centimeters, 4.9 inches. That was long. In fact, I made a circle so you can see it. You have to have, a flannel board or something to stick them on. And the 5 gigahertz is smaller. Now it goes back to that equation that was in the trivia question. It's the speed of light divided by the frequency gives us the size. We know the speed of light, it's a fixed, it's a constant. We know the frequency, in this case 2.412 is the specific frequency on the bottom channel. And then we do the math and it comes out to be this big. So the RF wave is physically that long. Now, one of the things we do with antennas is we make a quarter wave. So we take that 4.9, it turns into like 1.21, and that's the size of our antenna, or an antenna that can listen to this. So now we're done talking about that stuff. It's time for the analogy. And of course, in all analogies, they're wrong. But the purpose of analogy is to take something you either don't understand or can't see or can't visualize and turn it into something that's a little more easily recognizable. So we're going to talk about water. Now, I live in Utah. It's a desert and nothing grows unless you put sprinklers on it. I'm currently up in Wenatchee, Washington, and on the way here, you drive past the Pasco area where they have the Columbia River down in the riverbed, but all the land doesn't have any water because it's also dry. But when they pump it up there and put them on these big pivots, you can have lots and lots of growth, but you have to sprinkle the water on. So I'm using this analogy about water, and yeah, it's not true. RF isn't water. It doesn't come out in droplets, but it allows us to visualize what we're talking about here. So think water, but it's really Wi-Fi. So how to measure how much water or rainfall lands on the place you want? I did a podcast once and interviewed a guy who makes this little electronic potato. So actually a little sensor that's shaped of a potato. You plant it in the fields of the potato. It measures the moisture in the water, and it uses radio waves to tell the farmer it's time now to put your sprinklers on. Most people don't have those kind of little electronic potatoes. They use something like this little rain gauge, where the water that gets spread in the air lands in a little cup, comes down, and you can measure how much it is. What we want in Wi-Fi is we want signal to hit our clients. And we need the clients to get enough signal that they have an SNR that clears what they need. Now, we've talked a lot in the past about MCS. In fact, my last slide on this deck is another MCS table because I love MCS. But MCS comes from this. So if we know how much SNR we have, then we can have a pretty good estimate of what our MCS is going to be, and thus see how happy and healthy our clients are. Measuring how much water you get. So the sprinklers in this analogy are the different antennas. Now we can get sprinklers that go back and forth, like the one in the middle. We can get some that spray in patterns. We can get some that just spray in a circle and make omni antennas, directional antennas. And you can see that if you design a sprinkler to cover a certain area, it covers the area. If you turned up the pressure on the water, it would go further. It wouldn't necessarily give you more water. It would make the water you had go further, but would also mean it would spread out the amount of water that anyone would receive. Just because you turn up the pressure and it goes further, the same amount of water doesn't give you more rain in a certain area. If you focus the water, like I'm sure some of you have gone out and watered your lawns with just a hose and your thumb on it, and you can make all the water of the hose go to one place, but then it doesn't go anywhere else. Or you can spray it and it goes everywhere, but it doesn't fill anything. And again, we want SNR to be how much water we actually receive. So staying with this same theme, I'm sure you've seen Wi-Fi that looks like this, where they just take a whole bunch of APs and go AP, 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 and now we have lots and lots of water. And this is why the analogy falls apart. It's not just about the water. We need to have special water. If each of these different ones had a different color and we wanted to capture only red color. So yeah, I'm showing you that I know the analogy is flawed because you just can't have lots like this. Wi-Fi doesn't work that way. So just to make you think that it's not a perfect analogy. Now, all antennas aren't created equally. We could have an antenna like the one on the upper left, where if you put 10 dB in, EIRP is what you get out, and you actually lose a little bit of energy. Or you could look at the one on the bottom right, where you put 10 dB in and you get more than 10 dB out. That's because it's focusing it. like a sprinkler, it'll take the water, and instead of spreading it all in one place, it kind of focuses it. Now, this week, and this is very timely, like just a couple days ago, a guy took the Ekahau antennas and fed the guy, Alexandru, I can't even pronounce his last name, Vrabie, works for a company called NetShape out of Bucharest, and he's using this antenna pattern editor software, and he just imported in the pictures, and they turned them into nice 3D models. Yay, we like 3D models. These look really cool. But just realize, like Chuck said, these are in dB, so you can't say that's the pattern in the real world, because the pattern in the real world is the net effect of the power coming in and that. But it's the shape of the antenna pattern, and they're cool to look at. I like the one on the left because look how focused it is. It puts the signal where I want it. And it's on the antenna, it's doing a circular pattern, but it's not wasting its energy going up and down. It doesn't have a hole in the bottom like some Wi-Fi antennas that do look like a donut. There's a little hole in the bottom. On the right side, there is a directional antenna that you might put in a warehouse and you can aim it. Just like sprinklers, we can design an antenna that's either effective to cover what we want or ineffective and it covers what we don't want. And that's the number one rule with antennas: cover what you want, don't cover what you don't want. Because if you didn't want it to go everywhere and it does, you're just wasting all that water and you're getting stuff wet that doesn't need to get wet and you're wasting the energy. So let's talk about receive aperture. This is a concept a lot of people don't get. And if you don't get it, you should. I'm just saying, let's talk through this, because this is the why 2, 4, and 5 gig are different. Now, for each of these circles, if you look just at the rim, that's the difference between the low end and the high end. The low end is the slightly bigger one, and the high end of the pattern is a slightly smaller one. And 2.4 gigahertz, you can see there's a little teeny band. 3.5 has a slight band because it's not a very big band. It doesn't, 3.5 is not, we don't have a lot of space in 3.5. In 5 gigahertz, we have more space, so we have a bigger band. And in 6 gigahertz, we even have a bigger band because the difference from the low end of 6 gig to the high end of 6 gig is fairly significant. So, oh, and then I just threw up 60 gigahertz to see how teeny it is. So, if you have a 2.4 gigahertz antenna and it's spraying 2.4 gigahertz of water sprinkled in some place, this is the size of your rain cup that's catching the water. Think of it this way, little thing, and this is how much water you can catch off a 2.4. This, by contrast, is the amount of water you catch off of 5 gig. It's small. Oh, I've got to turn it around so you see them. It's smaller. How much smaller, Jim?
About half as small, 6 dB.
6 dB. So it's physically half as small, but that's the diameter. We actually have 4. You could put 4 of these in here, which is why it's 6 dB. One of the trivia questions that I put up, Heather didn't use, it's okay, was what's the difference between a circle with a diameter of 1 inch and a circle with a diameter of 2 inches? And the difference, actually, if you run the math, is 3.97. That's how much difference there is. So just because it sounds like 5 gig is twice as small as 2.4, it actually receives 4 times less energy. The little cup receives 4 times less water. 6 gigahertz is going to receive even smaller. You can see it on the screen. Plus, I want to just give me something to hold when I was talking. What about 60? It hardly catches anything. But the benefit of 60 is we can get a 30 dB antenna that's only this big. So we can have a very small form factor and still get a 30 dB increase in what we captured. The reason I'm showing these, the reason we're talking about antenna aperture, is it's not because 2.4 somehow magically goes further than 5 gig. I hate it when people say, oh yeah, 5 gig doesn't go as far as 2.4. That's a flat out lie. That's not true at all. If I had a 2.4 and a 5 gig radio right here, and they both broadcast at the same time, when they hit the moon, They would hit the moon at the exact same time, at the exact same distance, with the exact same amount of water. The difference is on the moon, the 5 gig would have less water because it has a smaller receive aperture. If the same two APs broadcast and went all the way to Jupiter, they would hit Jupiter with the exact same amount of energy at the exact same time. The difference is my receive aperture is smaller, so I can capture less energy because that antenna physically is smaller and receives 4 times less energy. The amount of water that hit Jupiter is the same as the amount of water that hit the moon. It's the same as the water that left. The difference is what I receive it with. So when we are designing 2.4 versus 5 gig, the easiest answer is transmit less on 2.4. And then, or you could do the reverse, transmit more on 5 gig. So the result is the 5 gig client device receives the same amount of water as the 2.4 because it's pushing out more. Think about it. Okay. Now we need to talk about the other side of this. This is flow control. If you wanted to fill up a 55-gallon drum, you could go with a 1/2-inch diameter pipe or a 5/8 or a 3/4, and you can see it takes less time. There's more gallons per minute. If you have a 2-inch pipe or a 1.5-inch pipe or a smaller pipe, this graph shows how many gallons per minute we're putting out. This is not pressure. This is water flow. And we do not have a control over water flow with RF. Again, good analogy. You can visualize the sprinklers. You can visualize the cups catching the water, but we can't control the flow. We can only control the pressure. And that will tell us how far it goes. But as we saw with most antennas, if you are sending it a place you don't want it to go, you're watering the neighbor's lawn, but your lawn's dry. Turning up the pressure and covering more neighbors doesn't give your people any more water. We don't have the flow control. Thus, the analogy falls apart, and you can't, don't go telling everyone, oh yeah, it's just like a sprinkler. It's not, but it gives us an idea that we can visualize the difference between a directional antenna and receive apertures, etc. So how the professionals do it. On the left, we have a little plastic. Actually, I looked it up. It cost $10 at a DIY store. A $10 sprinkler that's going to send water in a circle. It's made of plastic. It even has a quick disconnect. Or on the right side, for about 6 times as much, 7 times as much, it doesn't have a quick disconnect. You have to have a pipe to put it on. It's called a rainbird, and it goes. Yeah. It's made of brass, though. It's made to last a long time. They both do the same thing. They send water in a circle. The one on the right can send water in a much, much bigger circle. It can handle a lot more pressure, and it's made of quality materials. So when you're installing APs, you don't necessarily go down and get a little, I don't know what name to use, TP-Link, some cheap little thing that only costs $10. You spend more money, lots more money, because you want to get something that's going to last a long time. The quality of those antennas, as I referred to a little while ago, if you have an antenna that just gets sprayed everywhere and it's not very clean, you're wasting that energy and it's not going into the cups. It doesn't hit your clients. So use high quality antennas, use high quality APs if you want the water to go where you want it to go, if you want your clients to get their full fill of SNR. Additionally, it lasts longer. Yes, you can put cheaper gear in the other places and they work. I'm not saying they don't. I just built a new house. I put Ubiquity in everywhere because it works for me. It fits my goal. And I'm probably not going to leave it very long because there's Wi-Fi 7 coming soon and I want to change that. So I had to throw in at the end here a MCS chart because you always have to have MCS chart. What we're after is, how do we get higher data rates? We have higher SNR. How do we get higher SNR? We capture more water. And if we have a 5 gigahertz or a 6 gigahertz, we need to send it a little more. when we're talking about 5 versus 6, these are very close. The sizes are very almost the same, very little change between them. But there's some rules in 6 gigahertz that are in addition to what we have in 5 gig. In 5 gig, as we double from a 20 to a 40, we end up listening to twice as much noise because we have made a wider channel. We transmit on a wider channel, we receive on a wider channel, but we also are listening to an extra twice as much noise. So our SNR drops by 3 dB, not because the S changed, but we made more N. We listened to more noise, we lost that. In 6 gigahertz, under the wisdom of the FCC, and I appreciate that they did this, they allow us to double the size of the channel and not lose that extra 3 dB. They didn't actually make us not lose the 3 dB. We actually lose the 3 dB. We're listening to more noise. What they allowed was our transmit power to offset that. So now if we could transmit at, I'll just use 10 as our transmit power on 20 megahertz, we can now transmit at 23. So even though the noise floor, we're listening to twice as much noise, we offset it with the transmit power so our clients can still receive that. That's one issue we have in 6 gig, allows us to transmit and maintain that received energy. The amount of water that's hit on the 6 gigahertz can stay the same. But they also implemented a rule saying clients have to be 6 dB down from the AP's max. So our clients, when they talk back to the AP, are going to be throttled, and so they don't have the same distance, meaning APs can talk down to clients, which is great, and use that extra power, but clients will always be throttled at 6 dB lower than the clients. So our design circles have to be smaller, not because the APs can't hear the clients, it's because clients can't transmit the same power on the way back. So, key takeaways. Size matters. It's not the channel and the frequency, it's the size of the receive aperture. Yes, 2, 4, and 5 gig go through materials differently, slightly differently. The big difference between 2, 4, and 5 is the receive aperture of the clients. There was a company, I won't bring up their name, who thought they could beat this by making their APs on the receive side have 2 antennas that merged together so they receive double the receive aperture. It didn't actually work that way, but it's a cool idea. They were thinking about the issue. So, questions? I didn't see all the Q&As. There's obviously a bunch of chats going on. So,
yeah, no problem.
Jim, you've got the questions. You want to ask away?
Great job, Keith. And love all the content, particularly around receive aperture, because I think that's a concept that's not discussed very often. And, the kind of, we substitute, a belief that, hey, 5 gigahertz doesn't travel as far, or, it's a property of the transmitter or the
it's easy to say
itself.
5 gig doesn't go as far. It's harder to understand it actually does, but our receive clients are a little different. So,
yep. So we have some good questions in here, and I want to invite anybody in the audience with a question for Keith to use the Q&A panel. Manish has a question, and Manish says, given the same transmit power, will the 5 gigahertz and 2.4 gigahertz signals travel the same distance? And I think we
Yes.
answered that. Or 5 gigahertz signal would need more TX power to send at the same distance.
No, it's not the distance. That's the point. They go exactly the same distance. The difference is the 5 gigahertz would capture less water because it has a smaller hole. So in order to give it more water, you'd have to then double that. Actually, quadruple. You have to go by 4. That was kind of the whole point. Thanks for asking the question so I could review it one more time.
And overcoming that, there are things you can do on the receive side with multiple antennas and using digital signal processing to combine those signals. But there's if you're doing it for 2.4, you'll probably do it for 5 gigahertz too, right? And you still end up with the same differences for the most part.
And the reason you want to adjust the transmit power is you don't want the 2.4 to go that far, that loud.
Yes, that's correct.
And so you're controlling the size of this, how much area gets wet, not whether or not because I don't want the green water to go where I have red water kind of thing. So if I can control how far it goes, then I have, because I only have 3 channels, so I have to have them not overlap each other. And 2.4 has a tendency to overlap a lot. And so if we can control that in any way.
Quick one from Wayne, and we kind of transitioned into this. So he says, so why is 5 gigahertz faster then?
Why is it faster? Oh, that's an easy one. Because this is simple. We did another episode like a year ago. When you have a digital encoding, you're taking a digital 1 or a 0, and you're going to put it on a radio wave. Each radio wave has the ability to carry a little bit of information. When you have 5 gigahertz, you have twice as many radio waves in the same size. So I can have a whole bunch of these next to each other, and each one carries a digital information, compared to the 2.4 has less ups and downs, and so there's less data that I can deliver in the same amount of time. So the 5 gigahertz, it's not going faster, the waves don't go any faster. I can carry more data because there's more opportunities for a phase change.
Yep. And you can also carry even more data because you can use wider channel widths. You can go out to 80 megahertz, 160 megahertz. You can use 802.11 AC, it's modulation, which you can't do in 2.4. So,
but it's not the magic that we think going to double or even double spatial streams. For those of you who want to go to wifiu.com and follow up, there was a session we did on a single transmission last year where it shows the actual net change in throughput isn't double, because when you think about each transmission takes time, there's a dead air time, and then a preamble, and a header, and a frame body, and an MCS, and the little carrier is that we actually carry our data is pretty small. And from a time standpoint, whether you transmit that double fast with double wide or 2 spatial streams, all of the overhead is the same size. So we don't get an actual doubling of, we're not twice as efficient. We're only twice as efficient inside that little carrier. The rest of all the overhead of 802.11 is still there. So that'd give you a reason to go to wifiu.com and check it out.
Absolutely. Forrest with a question, clarification. Did you say it's the law that clients transmit at half the power of an AP?
It's not a law. And it's not half the power. It is a rule that says in 6 gigahertz, clients have to transmit 6 dB down from the maximum that an AP can transmit at. And we're still in early days when it comes to 6 gigahertz. Clients, sometimes they implement that differently. Is it 6 dB down from what I heard the AP transmit, or is it 6 dB down from what the AP's able to transmit, but maybe right now is not transmitting? So yeah, that's kind of still all over the map.
That's a good point, because an AP can be pretty dynamic in the transmit power it's using in the real world, depending on the number of spatial streams and the channel width and the MCS it's using. All those things may cause it to use a different transmit power.
And then what's the client supposed to do? So client manufacturers, some to get approved early on, they were very conservative. And they said, whatever the AP send to me, I'm going to send it back low. And so an AP might have dropped its transmit power for another reason, and then all the clients have to do that. Or others would just say, well, what's the max he can do in this place? And I'll just put my max 6 dB below his max, and I'll transmit all the way I want. Yeah. And some really big manufacturers haven't went to 6 gig for some of those reasons.
Yeah. Anders with clarification that 6 dB down is just in 6 gigahertz low power mode, low power indoors. Not sure about other modes. It does apply to standard power as well. So, And maybe one last
Wait,
quick
what's
question.
Anders doing talking about standard power? He doesn't have any standard
Oh
power.
yeah, they don't have any of that yet. Last thing from your Mund, friend of Seven Signal, says, how many times in your life, Keith, have you talked about the Utah water system?
All the time, because it's really sad. Hey, we don't have any water. You walk out in the woods near London, you get wet shoes because you have moss everywhere. So yeah, we just have dirt, but we have really pretty rocks. You know, people come around the world to see our rocks.
There you have it. All right, great. Well, thanks a lot, Keith. Another great one. And Heather, I think we can transition now.
All right, good stuff. Well, thank you again, Keith. Really great session. Lots of great feedback. Anders is like, how about salt? You got salt out there too, right? All right. Well, Eric, you can come out of hiding now. There he is. Wonderful. Welcome back.
Thank you. Thank you. Glad to be here. Thank you, Keith. That was awesome stuff. I'm definitely going to be brushing up on my physics by watching this again and learning more. Now let's take a look. This is 7 minutes with 7 Signal. This is where we take a couple minutes to, apply a little bit of what we learned today and review how our 7 Signal system maybe can kind of identify some of the things that we've been referring to. So let's go ahead and share our screen here, right there. Hit the share button and just give me the thumbs up if you can see that. All right, so let's take a look, guys. So right here, remember, a Sapphire Eye is a client. All right, and so as a client, we put it somewhere, and then that client is going to connect to a variety of access points. And we're doing these measurements all the time, all the while. And so in that manner, we're able to see, okay, for all of these access points, we're measuring the signal strength. Look at this. We can detect these fluctuations in signal strength. Look at where this one just kind of dropped off, dropped off the planet, so to say, all the way down here. Now, why does that happen? Well, it could be for a variety of things. It could be a barrier to propagation, like we were talking a little bit about today, or it could be one of those pesky little algorithms, inside your controller that's fluctuating the transmit power in order to try to accomplish something. And so it's very important to measure. This is what we want to see. We want to see it kind of nice and steady like this. But when we see these fluctuations, then again, we know what's going on. Now, just going a little bit further, we're also measuring the signal to noise ratio. So again, there could be something that enters into the environment that then raises the noise floor. We don't know. We can't see it, but 7 Signal can. And so you can see the number of dB difference here with regards to the signal to noise ratio. And we want to make sure that we've got a nice robust SNR in order to achieve the speeds that we want to achieve, get that good MCS. All right, and then down here, we're looking at the channels. And I know Keith would just love looking at this picture of a nice static channel plan. All right, let me show you one more thing, guys. Remember, we can't see or hear Wi-Fi, but when we go into the 7 Signal system, we do have a spectrum analyzer, which attempts to help us see what's going on in the air. So this is our 2.4 gigahertz spectrum analyzer. And this is a waterfall chart, and you can see how, channels 1, 6, and 11, we have time on the y-axis, and kind of like a Wi-Fi spectral slug leaving a trail of energy behind, you can see the energy in the air. You can also see some Bluetooth striping across left and right as well, talking about how we have to share with these different, the unlicensed band. So let's just go down a little bit further here. Here you can see maybe a low data rate, right, guys? I mean, look, we're not using the full 20 megahertz wide channel of channel 6 here. We're just using like a sliver of it. So low data rates may be in effect from slow clients. So that's, really kind of neat to see. And then we get into 5 gigahertz and we can see the activity as well. Again, starting at the top, the slug is leaving a trail of energy behind. So that's what I wanted to share with you guys today. We're talking about energy. These are things that we can't see, we can't hear. These are, Keith had the wonderful analogy with regards to the sprinkler and the water. We use these analogies that are not perfect, but we use them in order to help wrap our brains around things that we can't see or hear. So in that manner, I just want to remind everybody out there that you and me, we can't see or hear Wi-Fi, but 7 Signal can. Thanks for joining us, everybody, and have a great one.